investigate some more on the concept of phase angle. You know, this is how I write the general form of a sine or cosine wave, a sine of this angle. This is called the phase angle. It's a function of location and time. So basically, you understand that if we know what the phase angle is, then the waveform of this sine wave or cosine wave is determined. So the phase angle really is of crucial importance to determining this wave. We learned one way to write down this phase angle. It's k times x minus vt, and here k, as we know, it's called the wave vector. It's called a vector because it actually has a not just a magnitude but also a direction. The direction is defined to be the direction of propagation of the wave. So if it's x minus vt, for example, we know the wave travels along the positive x direction, so k is defined to be a vector moving along the positive x direction. And the magnitude of k, as we know, is 2 pi over lambda. This is not the only form to write down the phase angle. Let us look at some alternatives. If we plug this in, if we move that k in, then we have kx minus kvt, right? What is the combination of k times v? Okay, let's take a look. So k times v, because k is 2 pi over lambda, so that's lambda, I'm sorry, 2 pi, and then v over lambda, right? What is v over lambda anyway? You know, lambda over v is equal to t, the period, right? So v over lambda is just 1 over t, the period. Now, that looks familiar, 2 pi over t. What's 2 pi over t anyway? 2 pi over t, isn't this the angular frequency of the oscillation of each oscillator inside that wave? So that really is just omega, isn't it? Okay, I can also write this down as 2 pi f. F being the frequency. Okay, f is the frequency of the wave, 1 over t. It is the frequency of each and every one of the oscillators going up and down to form the wave. Now, kv equals omega. And if I plug that in, I get a new expression equivalent to the first one. That's kx minus kvt. That's omega t. Okay, this is a very common form used by physicists. Kx minus omega t. We're going to use this a lot. That's how we express the angle. We can also write this more explicitly by plugging in the value of k and omega. We know k is 2 pi over lambda and omega is 2 pi over t. So I can take that 2 pi out. Okay, k is 2 pi over lambda, so what's left is x over lambda. Okay, and what's over here, omega is 2 pi over the period t, so 2 pi comes out, so what's left is time over period. This expression is also very interesting because it highlights the symmetry between t and lambda. You know, as a wave propagates, the phase of the wave is determined by both the location of the oscillator and the time. Okay, the period over time for each oscillator is t, and the period over space is lambda. Okay, lambda tells you if 2 points are a distance lambda apart, then at the same moment, these 2 points have exactly the same phase, so they have exactly the same displacement. So this is the period over space, and this is the period over time. So the wave is periodic both over space and over time. I can write this. Okay, so what I have here are 3 of the most common expressions for the phase angle in a sine or cosine wave, sinusoidal wave, k, then x minus vt. This expression highlights the connection between x and t. X and t must come in a combination like that so that you know the speed of the propagation of the wave is v. Okay, this expression is also very commonly used because it's probably one of the easiest to write, just kx minus omega t. There are no parentheses. K is the wave vector and omega is the angular frequency. And again, the last expression highlights the symmetry between time and space. So this is the periodic wave both in time and in space. Please make sure you are familiar with all these expressions, along with the fact that k is 2 pi over lambda and omega equals k times v. Okay, now let's look at the speed of a particle making the oscillation in a sinusoidal wave. please make sure that you do not confuse between the speed of a particle going up and down on the string and the propagation of the wave on the string. Let's say here is a snapshot of the wave on the string. Okay, the wave propagates this way, right? V. And we know how to calculate V. In fact, it is the square root of the tension divided by the linear mass density. We'll come back to that. But what about the speed of a particle? Let's say this particle. Let me use a red color. Here's a particle. Okay. This particle goes up and down, right? How do you find the speed of this particle? You know, this particle goes up and down. It has its own speed. In fact, as a variable speed, it doesn't have the same value because, you know, it's a simple harmonic oscillator, and any simple harmonic oscillator speed is not a constant. The speed of wave propagation, v, now that is a constant. Okay, so please make sure you don't confuse between these two speeds. You know, this coordinate, that is the y coordinate, right? This is the x coordinate. So as the particle goes up and down, its y coordinate changes. Therefore, the speed of the particle going up and down, or more precisely, the velocity of the particle going up and down, we call it Vy, okay, just to make sure it distinguishes from this V. This V is the speed of the wave propagation. Vy tells you how fast the y coordinate of this particle changes over time. So that really is partial y, partial t. That's how we define it. At a given location x, okay, I only take derivative with respect to t, keeping x fixed, which means I'm focusing on this one particular oscillator at this one particular location x. I do not shift from point to point, since I'm only interested in the motion of this one particular oscillator, so I don't change x. And so what is that equal to? Well, we know y, right? Y is a sine times the phase, sine of the phase angle, so we can plug any of these in, and we can actually solve for y. Okay, for example, if I plug this in, okay, so y equals a sine, and then kx minus omega t, right? If I take a derivative with respect to t, what do I get? Well, first of all, sine becomes cosine when you take derivative, and also there is a negative omega coming out, so it is negative omega a, and then cosine kx minus omega t. Alright, so you see, Vy, the velocity of this oscillator going up and down in the y direction, obviously does change over time. How does it change over time? It changes over time in a sinusoidal fashion, like a sine or cosine function. And remember here, x is fixed because we're looking at this one oscillator, not any other oscillator. So that kx basically just a constant. So over time, it changes like cosine omega t. So you see, it is a simple harmonic oscillator. Okay, what is the magnitude of the maximum velocity? Well, that will be omega times a, right? So Vy maximum is omega times a. Is this any wonder that it is equal to omega times a? Well, not really, because remember, each of these oscillators is a simple harmonic oscillator in the y direction, oscillating in the y direction. We've studied that before, right? How did you find the maximum speed? Well, that was equal to angular speed, or actually rather angular frequency, times the amplitude of oscillation, right? The amplitude of oscillation is a, so isn't that omega times a? So that makes perfect sense. Okay, I can even find the acceleration of this particle going up and down. All I have to do is take one more derivative. That's what I will find. Okay, so that will be the acceleration of this particle going up and down. In fact, it's easy enough. I can write down the expression directly. I just take this expression and I take one more time derivative, right? So a y, what is that equal to? Well, you take a derivative with respect to t, again, keeping x is fixed. So cosine goes back to negative sine, okay? So when you do that, you have negative sine, so this becomes positive, but don't forget you have another negative omega sticking out, so the answer is negative omega squared a sine kx minus omega t. That is the expression for the linear acceleration of this particle going up and down. Now, what is the greatest value? What is the magnitude of the maximum acceleration for this particle? That's omega squared times a. And that, once again, is the expression that we got before for the maximum acceleration of a simple harmonic oscillator. So once again, you realize that this wave consists of many such simple harmonic oscillators going up and down. Okay. So that is a general discussion about simple harmonic waves. Now, going back to the expression that we obtained before for the speed of the wave on a string. We obtained this expression by solving the wave equation, remember? And in order to satisfy this wave equation, we find that v cannot just be anything. The speed of the wave must be equal to the square root of tension F over mu. Their textbook uses T for tension. I don't want to do that because that confuses with the expression with the symbol for period T. So this F represents the tension instead of T, the symbol used in the textbook. Okay. We got this expression by matching the two sides of the equation, so that's a mathematical thing, okay? I want to have a physical discussion as to why it makes sense to have V equal to square root of F over mu. Okay, first of all, you see the unit works out very well. F, that is Newton, okay? You break it down to the standard, basic units of kilogram meters per second squared. You divide it by mu. What's mu? Mu is mass per unit length, okay? That's kilogram per meter by definition. You take the square root, nicely you get meter per second. Okay, so the unit certainly matches. In other words, if I were to tell you that the speed of the wave depends on two things, the tension in the string and the linear mass density, then simply by using dimensional analysis, you can tell me that it's got to be square root of F over mu, maybe multiplied by a numerical constant, say 2 or 1 or whatever, but it's got to be something times square root of F over mu. That's what we got. Okay, so that makes sure that we make sure the unit matches. Secondly, why does it depend on F and why does it depend on mu? Okay, think about it. If I want a wave to propagate fast, okay, let's see here, we got a wave on a string. I want a wave to propagate fast. How does the wave propagate? Now remember, a wave consists, has to propagate in a medium. The medium consists of a whole bunch of oscillators, right? Each segment of the string is an oscillator. If you want a wave to propagate fast, then you want oscillations to move quickly from one oscillator to the next and then to the next to the next, right? So that when this oscillator starts to oscillate, immediately the next one feels it, the next one feels it, and so on. Okay, obviously, you want a strong connection between neighboring oscillators, right? In other words, neighboring segment of the string. What is the connection? What makes these segments connect to each other? Well, because there is a tension, right? There is a tension between them. So obviously, if the string is under a lot of tension, then this oscillator will pull the next one with a much greater force, and therefore, once it moves, the next one is going to feel its motion immediately, and then the next one immediately, and the next one immediately. So it is clear that the greater the tension, the faster the speed of the wave. That's why, as the tension F increases, so does V. Okay, now, is the tension the only thing that determines the speed of the wave? Well, not quite. If I consider two strings, okay, under the same tension, but one is a lot thicker than the other, a lot heavier than the other. Let's say, the string is that heavy. If a string is that heavy, then under the same tension, each segment is a lot more massive than before. So even if they're driven by the same tension, they're not going to oscillate up and down that fast, right? Because there is more inertia, there is more resistance to acceleration. So obviously, when the inertia increases, the speed of the wave will decrease. Okay, so the question is, how does one represent inertia in this situation? Usually, inertia is quantified by mass, right? But do you think it's a good idea, it's reasonable to use the entire mass of the string as a representation of the inertia? Well, that doesn't make any sense here, does it? Because what if the string is infinitely long? Okay, imagine, this is the free end of the string, you hold it and you wiggle it, right? But the string extends to infinity. What's the total mass? Infinity. Does that mean there is no wave riding along it at all? Does that mean the speed of the wave will be zero because the inertia is infinite? That doesn't make any sense, right? What really should be considered is not the total mass of the string, but rather how heavy each segment is. In other words, the mass per unit length of the string. That will be a more realistic, reasonable representation of the inertia. So that is why we use mu, okay? So you see, it makes sense to enter tension and enter mu. Generally speaking, any elastic wave, okay? Wave on a string is just an example. any elastic wave, it is always the speed of the wave is determined by two competing factors. One is the elastic parameter. The more elastic the medium is, the faster the wave propagates. And the other is the inertia parameter. Okay, the more inertia the medium has, the slower the wave. Okay, so it's always the competition between the two. And it turns out that the speed of the wave in any elastic medium can always be represented by the square root of some sort of elastic parameter divided by some sort of inertia parameter. And what we have here is the square root of tension over mu. That is just one example. There are other elastic waves, such as, for example, the longitudinal wave in a string. In a spring. Okay, this is a transverse wave, also longitudinal wave in a spring. And in that case, the speed of the wave is not quite f over mu anymore, but it's something analogous. It's always some sort of elastic parameter over inertia parameter. And when we discuss the speed of sound, okay, in another chapter, we also enter a discussion of the speed of the sound propagating in a three-dimensional medium. Okay, in that case, you will also see something similar for the speed of sound, some sort of elastic parameter over inertia parameter. Of course, you know that sound is a three-dimensional wave. It propagates in a three-dimensional space, therefore, we shouldn't be using linear mass density anymore, right? Not mass per unit length, but rather what? Well, how about mass per unit volume, the regular three-dimensional density, right? And then what about the elastic parameter over there? Of course, we can do all the calculation, but if we don't have to do any calculation, we already know have some idea about the speed of the sound wave, that means we have a better physical understanding of the situation, right? We're not just relying on mathematics, are we? Okay, the elastic parameter. Okay, now in the case of a sound wave, you have to take air and you compress it. Okay, if the air is hard to compress, that means it's very elastic, right? It's just like a spring with a very large spring constant. And if it's soft, it's easy to compress. It's like a soft spring and it is less elastic. So, if you take some air, you want to compress it, what determines how hard it is to compress it? Well, if the air is under a lot of pressure, okay, then of course it's strong, it's hard to compress it. If you trap high pressure air in a cylinder, then you know it's difficult to push the cylinder in, right? Because the pressure inside is already pretty high. So, it might be a good idea to use the pressure in the air as a measurement of its elasticity, and use the density of air to serve as the inertial parameter. So how about this? Speed of sound would it be something like the pressure over the density? Okay, we don't know, of course. It is, however, a very good educated guess. And you can even see for yourself that the units of p over rho and the square root are actually correct. It gives you meters per second. Okay, is this a coincidence? We don't think so. As a matter of fact, when we do a mathematical derivation for the speed of sound in air or in any elastic medium, we can find something very close to that. Okay, so what we did here was we sort of figured out the speed of sound without going into all the math details, because we have a good understanding of what determines the speed of sound. It's a combination of how elastic the air is and how dense the air is. Okay, we'll get back to that in the next chapter.